Hi, I'm Sergey, and I'm the author of Embedded Networking Guide. In this video, I'm going to walk you through several chapters of this guide and implement a web UI dashboard on STM32 development board from scratch. I'm going to use two tools, the Cube IDE and an open source Mongoose library, which is the best way to code networking functionality on microcontrollers and other embedded devices. So let me start. Here, what I have on my screen, an opened guide published on GitHub. I have a Cube IDE open, an empty one. I have a terminal, and I have a microcontroller board. This is STM32 connected to Ethernet and connected to my workstation. So let me start. I open this guide and I jump straight away to the section called Skeleton Firmware. So at the first step, what we're gonna do, we create a minimal skeleton firmware that does nothing but logs messages to the serial console. And when we've done that, we'll add networking functionality on top of it. So what I'll be doing here can be done with any Ethernet-enabled ST board, and I'll follow this guide step by step. So step 1, start CubeID, choose File, New STM32 project. I click on Create a new STM32 project. That opens a target selector window. Step number 2, in the part number field, type microcontroller name, and that should narrow down the list at the bottom right. Then click Next. Okay, so this is the part number. I type H743ZI. This narrows down the selection to just one entry and click on that. I click Next. Okay, the guide says, in the project name field, type any name, then click Finish. Answer yes if a pop-up dialog appears. I type H743 as the project name, click on Finish. Dialog asks me, do you want to apply default configuration? Click Yes. So now Cube configures my project. Let me see. Step number 4, a configuration window appears. Click on Clock Configuration tab. Find a field with the system clock value. Type a maximum value. Hit Enter. Answer Yes on auto configuration. So on this step, we configure the clock, system clock to the maximum value. So I click on Clock Configuration tab, find where is this entry. So here it is. By default, it says 64 megs and maximum, here written in blue, 480. So I type the maximum 480 and click Enter and answer yes to answer OK to auto configure. So now Cube auto configures my clock to 480. Let's see what's the next step says. Step number 5, switch to pinout connectivity, then enable the UART controller and configure pins. See table above, choose asynchronous mode. Okay, now Cube configured our clock to 480 megs. I click on pinout and configuration, click on connectivity, look at the table above. I need to configure USART3 with pins D8 and D9. Okay, find where USART3 is. Here it is. I click on USART3. In the mode, I choose asynchronous. Okay, and I click on GPIO settings here and see what pins were selected by Cube. The pins are PB10 and PB11. My table says it should be D8 and D9, so I need to change the pins. Cube selected the wrong ones. Okay, I go to this window. I need to find PD8 and PD9. Here they are. So I click on PD9 and choose USART3RX, then do the same for PD8. USART3TX. Now the PD9 and PD8 should be configured as USART pins. And let me check this table. Yeah, so now we are fine. USART3 is configured to use PD8 and PD9 pins. Okay, let's go to the next step. The next step is click on Connectivity Ethernet, choose Mode RMII, and verify that configured pins are like in the table above. Okay, let's find Ethernet controller. Here it is. Click on Ethernet. Choose Mode RMII. And let's check the pins that were selected by Cube and compare them with our list here. Okay, we can see that two pins are wrong. So we have to have G11 and G13 pins. And we have PB pins instead. So, okay, let's find PG11 and PG13. They are on top of the microcontroller. Here they are. PG13. I click on PG13 and select Ethernet TXD0 and click on PG11 and also select Ethernet TX enable. Okay, so now our pins are okay. The next step, look up the LED GPIO and configure it for output. Okay, LED, there are 3 pins on this nuclear board, B0, E1, and B14. Let's use B0 as an LED. So find B0 pin. I think it's at the bottom of the microcontroller. Yeah, here it is. Click on B0 and select GPIO output. All right, I think we are done. And the next step is click Control S to save the configuration. And this generates the code and opens main.c file. Okay, I click Control S, answer yes. So now Cube generates the code to configure those pins that we have selected. And step number 9 says, navigate to the main function and add some logging to the while loop. Make sure to insert your code between user code comments. Okay, let me copy this piece of code. Basically, we are printing current tick number and then delaying for half a second. Let me find this loop. Here it is. And I just paste these 2 lines here. Step number 9, redirect printf to the UART. Note the UART global variable generated by Cube at the beginning of main.c. Typically, it's UART handle type def HUART3. Let's see where it is. Yeah, here it is at the beginning of the file. Copy it, open syscalls.c, find function write, and modify it in the following way. So let me copy this piece of code. Open core, sources, and syscalls.c. Find function underscore write. Here it is. And change it to 1 from the guide. So what we are doing here, this function underscore write is called whenever a higher level C library functions like printf, fprintf, fwrite, and so on are called. And what we are doing here, we are checking the file against 1 or 2. This is a file descriptor. So if we are writing to standard output or standard error, then instead we're just printing to the UART. That's what we are doing. That's what that piece of code does. And this technique is called IO retargeting or IO redirection. Okay, Step number 11, click on Run to flash this firmware to the board. I click on this green Run button. And click on OK. Click OK. The firmware has built, and now it's been flashed to the board. Okay, now we need to attach a serial monitor tool. On Windows, you can use PuTTY. On Mac and Linux, you can use a standard CU utility. So let me use CU. I type CU -line dev CU underscore USB. So this is the COM port device minus speed 115/200. Click enter. Okay, I see those messages printed on the serial console. So our skeleton firmware is ready. Now we have a minimal, bare metal firmware that only does logging on the serial console. Let's switch to the next step, which is to integrate Mongoose. By integrating Mongoose, we will implement a functional TCP/IP stack on our development board. So on step 1, we open GitHub repository and then click on mongoose.h, click on raw button, copy the contents, create the file mongoose.h and paste the contents into it. So basically with this step, we just copy this file mongoose.h to our source code. Click on mongoose.h, click on raw, and now I click on Control A to copy the whole file into clipboard, switch to cube, open, right click on includes, new file, type mongoose.h and paste the contents here. And I repeat the same for mongoose.c. So change h to c, copy, create a new file in sources, type mongoose.c, paste, and save. Okay. Next step, right-click on Core Includes, create a new file mongoose custom.h, and paste the following contents there. So let me create a new file in includes, mongoose underscore custom.h, and copy this contents here. So this is a configuration file for Mongoose library. We configure a bunch of options here. So this line says that we are going to use newlib build environment. Newlib is a C library that is used by ARM GCC installation, which is shipped by Cube IDE. So it's basically on all environments that where we use ARM GCC, we can use this configuration line. Then this line enable TCP/IP enables a built-in TCP/IP stack in Mongoose library. This line says that we should implement mg_millis for the internal timekeeping, and this enables a driver, a built-in driver for STM32 built-in Mac controller. So step number 4, let's include mongoose.h, switch to main.c file, find this section for private includes, add include mongoose.h, and before main, we should define this function mg_millis. Let me do that. So this is main, and this is the block before main. I paste this mg_millis function here. This mg_millis function just returns the current number of milliseconds since boot. Step number 6, navigate to main function and change the code around while loop this way. So let me copy this. So we should insert it between the user code begin while and user code end while. So here it is. So begin while and end while. I delete this whole thing and paste what I've copied. So let me explain what the snippet does. We create Mongoose Event Manager, initialize it, set the log level to debug. Then we initialize the driver, initialize network interface. We tell it to use this MAC address, 2345667, and to use a built-in STM32 driver. Then we enable Ethernet interrupt, enable TCP/IP stack, and in the infinite event loop, we just process network events. That's it. Step number 7, connect your board to the Ethernet. We already have it connected. Flash firmware. In the serial log, you should see something like this. Okay, let me flash it. Click on this green button, click OK. And let's wait until it's flashed. And here we go. So in the serial log, we see messages from Mongoose library that our board initialized TCP/IP stack and it got an IP address from the DHCP server. So the guide says if you don't see these lines with IP address and instead you see messages like this that DHCP discover sent, then most probably you just configured your Ethernet pins wrong. So double check your Ethernet pins. So step number 8, open terminal, command prompt and run ping against the IP address. So let me copy this IP address, start a new terminal, and then run ping. And as you can see, we can ping our board. So now we have a functional network stack running on our board. So all layers from 1 to 3, so driver layer, TCP/IP stack layer, and the library layer are implemented. But we don't have any application running on our board. So now let's skip to the next section, implementing the last layer, number 4, an application layer. And we will implement a simple web server. So to start, let's add a very simple web server that just responds with OK message to every HTTP request. So on step number 1, we need to add this single line after TCP/IP init. So this is the line TCP/IP init. And after this, we stick a single call mg http listen, and we give it this listening URL. So and the function, event handler function, is fn. So this line, it says please start http listener on port 80 with event handler function fn. And let's define this event handler function. It's part of the Mongoose library API. So we go here to the user code section, and after function mg_millis, we paste a definition for the function fn, which is an event handler function. So this function will be called by Mongoose library for every connection that got accepted by our listener. And this function will be passed many different events, right? So in this case, we ignore all the events. We just react on one event, which is mg event HTTP message that says, hey, you've got a new HTTP request coming. And for that, we just respond mg HTTP reply, which is another Mongoose library API function. We just print OK as a response. So that's it. That's how the simplest HTTP server gets implemented. I click on Flash, Click OK. And then guide says, open your browser, type board's IP address, and see the OK message. Let me do that. I copy the IP address, paste it here in the browser, and sure, I see the OK message printed. So now I have a functional, simple web server running on my development board. Note that this function, mg_http reply, as the last argument, it accepts format string, so it can print formatted output. It's like printf on steroids, right? If I open the documentation, so this is the documentation for HTTP reply. It accepts the connection, status code, additional headers. So we say that the status code is 200, which is okay. We send no additional headers, and we specify just OK as the formatting string. But we can also create a really complex output using this format string, CMG sprintf for the supported format specifiers. Most of them are standard, but there are two non-standard specifiers like %m and %m, which accept custom formatting functions. So basically you can print anything, and there are a bunch of built-in formatters, like you can print you can encode base64 on the fly. You can encode JSON strings on the fly. You can print hex. You can print IP addresses, and so on. And you can print your own. So you can, for example, create your own printer for your structure, for example, and print that everywhere. Like as a response to HTTP request or into a string, like anywhere. So it's a really powerful function. So that said, that with this piece of code, we can generate HTTP responses of any complexity. So how the whole thing works? Let me explain the whole receive flow so you'll understand every step. So when a browser connects to our board, the hardware on our board receives an interrupt and our Ethernet IRQ handler kicks in. IRQ handler reads frame from the DMA and copies that frame to the Mongoose receive queue. So let's take a look. This is our IRQ handler. It reads the frame from the DMA, and then it copies, it uses this function mgtcpapq_write. It copies that frame into the receive queue. And this is the receive queue. So this is the definition for the network interface. And this receive queue, it's a special single producer, single consumer, non-blocking queue. So it's safe to the IRQ handler to write that frame into that queue and to some other function from another task or another thread to read from that queue. So the MGR poll function in the infinite while loop here in our firmware, it constantly verifies whether we receive any data in the receive queue. So when it detects a frame in the receive queue, it extracts that frame and passes it on to the mgtcp_rx function. So this is the Rx function. This is the entry point to the built-in TCP IP stack. So that's the code that calls TCP IP Rx. We verify, oh, do we have anything in the receive queue? And yes, if we do have something, that we call this function mgtcp IP Rx, which is an entry point to the built-in TCP IP stack, and then we delete that frame from the queue. So the mgtcp IP Rx function parses headers starting from Ethernet, and when it detects that a received frame belongs to one of the Mongoose connections, it copies that frame data into the C receive buffer and calls mg event read event. So again, this is the part of the TCP/IP stack. And if we see that, okay, we belong to some connection, we just copy that data to the connection payload. And then at this point, the processing leaves the TCP/IP layer and enters the library layer. So Mongoose's HTTP event handler catches MG event read, parses received data, and when it detects that the full message has been buffered, it sends MG HTTP message with the parsed HTTP request. So here is a built-in event handler for the HTTP. So here we parse the buffer, and if we see that we've got the full request, eventually we call this function mg event HTTP message, and HM holds the parsed HTTP message. And that's where we hit our application code. Here, this call mg call mg event HTTP message calls our function, calls this. And yeah, we react to the HTTP message and we print the response. So, and mg HTTP reply, it crafts a really simple response. It prints the content and specifies a content length HTTP header. So this response goes to Mongoose's csend output buffer, and mgrr poll drains the data to the browser. So it splits the output buffer into frames, and then it sends them frame by frame. And it calls this txtcp function, which in the end it calls mgtcp IP driver tx function. So this is the last step, layer 1. So we're telling driver to send our buffer, so send our frame. And that's basically how the whole path works from receive to send. That's how Mongoose library works. You've seen all the steps. Other implementations like Zephyr, Amazon FreeRTOS TCP, WIP, Azure, they work in a similar way. The only difference is that most of them, they implement a BSD socket layer in the TCP IP stack, so the whole flow is a bit more complicated because it includes that extra socket layer, but the principle is the same. So, all right, so let's switch to the next step. So we want to implement a web UI. So far, we just created a really simple page with the OK response. And to illustrate that, how can you use this mg-http reply function to generate a more complex responses? Um, let me demonstrate that to you. So for example, we instead of the OK message, we can create a JSON response with, for example, the current tick number. So %m, we're gonna use a JSON formatted output, JSON formatted string. So g escape is a macro that creates a JSON formatted output from the string. So let's say tick and LLU. So output base 64-bit value with mg millis. mg millis returns the current tick. All right. So let me build this. And now if I uh, the go to the browser, refresh the page, I can see JSON message instead with the current value of the tick. Okay, so MGHTTP reply function is nice, but it's good for creating custom responses, but it's not good for serving files. And serving files is the standard way to build web UI. So the UI is split in two parts. First is the static part, which consists of a directory with index.html and other files, other resources like CSS files, JavaScript files, image files, and so on. And the second part of the UI consists um, of the server. It's so-called a dynamic part that serves REST API. So I'll show that to you how it works. So instead of using MG HTTP reply and responding with OK to any request, let's create a directory with index.html file and serve that directory instead. So Mongoose API function exists, MG HTTP served there for that. So let's change our uh, event handler to this. So I replace my event handler with this. So basically what we are doing here, when we get a new HTTP request, we call an API function mg HTTP serve directory to serve the whole directory from web root. So to serve a static home directory. And if we try to build that firmware, let me click on build, we should get a build error. So a build error says undefined reference to make directory function. So what it means, this is because mg HTTP serve directory function, it tries to use a POSIX API to open that directory /web root and to see are there any files in that. And that POSIX file system support uh, also uses this mkdir function. And since our firmware doesn't implement any support for POSIX file system, then we get a build error. So what are our options? First option is to implement that POSIX file system. And then uh, we can implement it using an external flash memory or internal flash memory, and then we can copy our web root directory with static files into that file system, and then our code, like that piece of code, will work. So this is way number one, and this is the complex way. That's the hard way. The other way, the easy way, is to use a so-called embedded file system. So by transforming all files in the web directory into C arrays, and then we can compile those C arrays into our firmware. So this way, all UI files are simply hard-coded into the firmware binary, and there is no need to implement a real file system. So let's go this way. So the first step is to tell Mongoose that we are going to use this embedded file system. So we add one extra option to the serve options. So we are saying, please use the file system, which is called mgfs packed instead of POSIX. And then in the mongoose custom.h, we should disable the POSIX file system and enable this in a packed file system. Let me open mongoose custom.h and add these two lines. And the step number 3, we should create a new file, packedfs.c. Oh, let me do that. So I click on new file, packedfs.c. And that file should contain those embedded UI files. I click on this UI pack utility, pack UI pack tool, So this is the web UI we are going to use. Right? I can edit any file, for example, a CSS file. I can add color teal to change things. And when I click on pactfs.c, this is a generated C file, right? I copy it and paste here. And I click build. And now it should build without errors. Yeah, it builds without errors. So let's review what the UI packer does. So as you can see, it has 3 files, which implements a very simple UI. Here it is. So very simple UI with LED control. So the index.html file, here it is. It uses main CSS file. It loads main.js file. So in main.js file here, it defines a button click handler. Here it is. And the button click handler, when clicked, it makes a request to the URL API LED toggle. And when the request is complete, it makes another request. So it calls this function getStatus, makes another request to API LED get, which sets the status element to the result of this API LED get request. So this tool, as you can see, it has a preview window, so which reflects any changes that we can make to those files, so we can experiment a little bit. And also it automatically refreshes the generated file. So in that generated file, as you can see, it has 3 C arrays, which correspond to these 3 files. And also this pactfs.c, it has 2 helper functions. One function is mgunlist. So this function allows us to scan the whole file system and to return all the names of every file. And mgunpack helper function, it returns the contents, size, and modification time for any given file. So Mongoose provides a command line utility, pact.c, to generate that pactfs file automatically, not like through this web tool. The example of this is makefile for device dashboard. So you can see an example how the pactfs can be generated automatically. So you can use it in your build system. So, but that example not only packs, also compresses files to minimize their size. But we are going to use this simple tool because it's easy. So now let's flash the firmware. Flash the firmware. And go to the IP address. Let's wait until it's done. Okay, and let's go to the IP address. And now we can see our UI. So when we click on the button, nothing happens. And nothing happens. Why is that? So we open the developer tools and see that when we click toggle, we have 2 network requests to those a toggle and LED get functions, and they return 404. They are not implemented. So these are in the JavaScript. So JavaScript calls these 2 functions, API LED toggle, API LED get. And as we can see, we return errors for them. So now what we need to do, we need to implement those API calls in our event handler function. So our event handler function is, you see it completely ignores the URI, the URL that we passed. So we always respond with the with index.html. So now let's copy this event handler function and replace our event handler with this more versatile event handler. So let's build it and flash it. Wait until it's up. Okay, it's up, and I go to the UI, refresh it. Now, when I click on LED, then I see that then I see that the status changes when I click on an LED. And when I open the device itself, here it is. When I click on LED, you see the LED reacts. It lights on and off. So let's see how that piece of code works. So in our code, we have two. So we have this HM, which is a parse HTTP request, and we have this function mg HTTP match URI. So we compare the URI that we received with API LED get. So basically, if we get API LED get request, then we return with the status. Then we call HAL GPIO read pin. So we read the value of the LED pin and return as the status. So we return either 0 or 1. And if the URI is API LED toggle, then we call HAL GPIO toggle pin. So we toggle LED, and then we respond with true. And for the rest of the URLs, we respond with the default handler. So now, as you can see, we've implemented a really simple a web UI that toggles an LED. And it's very simple, it's very simplistic, but this is the pattern that works for the web UI of absolutely any complexity. So there are two parts. So this part is the static part, JavaScript, CSS, HTML, and so on. And the static part, JavaScript, makes API calls. And we have to implement them here in the event handler function. So this is how any web UI works. And it's just a matter now of creating a professional UI interface using any JS, CSS framework, whatever you like, and then extending this part, API part, with the respective handlers, and that's what it takes. Now, let me show you how to repeat everything that we've done in Cube uh, in the make plus GCC environment. It's just 1 minute. So navigate to Mongoose WS demo. This is the page. You can get to it just by going to mongoose.ws and click on this evaluate Mongoose in your browser. And here, this is the simple tool that creates a project completely in your browser, right? So this simple LED control is exactly the same UI that we just did, and we select a board. So we select our Nucleo board and click continue. So it creates, instead of Cube IDE project, it creates a simple bare metal project. As you can see, there are the same files, but the project is like really small because it's bare metal. And as you can see, it uses only Mongoose library, and that's it. So this is the main file for it. And I click build. So when I click build, it just zips all these files into the zip file. You can download that zip and build manually if you want to, and sends to Mongoose WS. Mongoose WS site, it runs make, creates a binary, and sends back the firmware.bin binary here. So now I can download that firmware.bin. But I also can flash it straight away. So I can connect the serial console, and I can flash this firmware directly from the browser. So let me see how that works. So now flashing works. As you can see, the firmware takes 54 kilobytes. and now it should finish flashing, and you see we have logs. Also, this firmware blinks an LED. That's the difference with what we did. Our version in Cube does not blink. Oh, I have two utilities reading the serial logs, and that's why I've got like messed output. Let me kill one. So I close this one command line utility. So let me reboot the board. And the IP address here we can see is different because we're using different MAC address. So if I go to this UI, we can see the same interface, and we can blink an LED. So when I click on the toggle button, so the orange LED is blinking, and the green LED is what we can set over the UI. Right. The only difference between this project and what we did in Cube is that this bare metal project, it supports the TLS. It supports HTTPS. So you see this section in the source code, what is what it makes it like support a TLS. But we will discuss the TLS section elsewhere because like it's a big topic. But as you can see, this simple firmware with the TLS support only takes 50 less than 60 kilobytes on flash. So now let's click on this Start Over button and choose the Complete Device Dashboard. And again, choose this, our Nucleo board. And the structure of this project is pretty much the same, but the web UI is way more versatile. So when I click on Build, and click on Flash, you see the size of this firmware is way bigger because the UI is more complicated and bigger. The UI is defined here. So the only difference is that instead of creating event handler function directly in main.c, we put the event handler function in net.h and net.c. Here is the event handler function. And in main.c, we're simply calling it using web init. So now I think we are ready. So let's go and open the UI. And as you can see, the UI now is different, is a complete UI dashboard. So I can log into it using admin. And as you can see, this UI is way more versatile. So it shows the dashboard page, the device setting page. I can change values, I can save them permanently on the device. There is a firmware update section, which in fact it works. It's a completely functional firmware update, but I will not cover it in this video because it's also a fairly complicated and big topic to cover. So, but what I'll do instead, I will copy this UI into our Cube project, right? So, and I'll follow 3 steps. I will go and copy these 3 files, net.c, net.h, and pactfs.c. All right, so first let me start from net.c. I create a new file in net.c. I also create a new file net.h. Here, new file net.h. And copy the new UI in pactfs.c. We already have pactfs.c. We'll just ditch the existing contents and paste the new one. All right, so In main.c, what we need to do, comment out mg http listen and add web init call. So comment out mg http listen, add web init call instead, and add the include net.h at the top of main.c file. So include net.h, and now open net.h, modify HTTP URL port. Open net.h, modify URL port. So instead of 8000, just standard port 80. Okay, rebuild, refresh, and flash the new firmware. So now we are flashing the new firmware. Let me start the listener again. I'll probably need to close this web listener. Yeah, and open the command line listener. And now let me reboot the box to see boot messages. Okay, so this is the IP address. Let me open that. Okay, I see now our cube project runs this versatile web UI dashboard. So here we are. It runs the same UI. And as you can see, this UI is implemented here. So the main code in main.js. So I will not go in this video through how the JavaScript UI gets implemented. There are plenty of tutorials on that topic, but if you want me to cover that, I can. So that if you want to do that, please click on this button to join our Discord server and let me know. So this is it. That's the end of the video. That's what I wanted to share with you today. And again, to summarize what we did, we created a functional web UI dashboard on the ST development board from scratch. And I've explained everything, how the whole thing works, how the TCP IP stack works, how receive path works, how web UI works, how it's structured, and how to build simple web UIs and also complex web UIs. There is not much difference in the structure between them. So thanks again for watching this video and see you later.